Hello everybody, this is Mr. Maze. I'm coming to you through the virtual sphere. I've got my little, my 2-month-old here strapped to my chest, and we're gonna come in, we're gonna give you some advice. This is the Unit 1. That's supposed to be a U, not a V. Oh my gosh, that looks even more like a V now. Mr. Maze, come on. Get your letters right. Unit 1, pro tips. We're going to go with some pro tips for this unit, right? Because there's been a lot of content that we've gone through this unit, and I just want to give you guys some tips and tricks that you can go back over. This is everything you will have gone over with me in class on the day of the review, but some things to keep in mind. 1, the median. We have to keep the median in mind. We've been doing a lot with means and standard deviations, but there are a few things to remember about the median. 1, the median is always the 50th percentile. Always, always, always. Why? Because 50% of data points lie before it and 50% of data points lie after it. You can see I threw a little E on the end there for no reason. The mean is sometimes the 50th percentile, but it's really just an average, right? The median is never an average. Now, of course, sometimes you average 2 data points in the middle to pick your median, but the median is truthfully not an average of anything. It is just a center point. So keep that in mind. And anytime it tries to say, I give you a question, or the AP graders give you a question where like the median is the average of, don't even let them play with you, right? It's simply the middle. And we know that the same amount of values lie before the median as lie after the median. So remembering our box plot, this is a good thing to keep in mind. We know that every quartile and the min and max, each part of that holds 25% of the data. 25% of the data points, right? Not the values of the data points, just the data points themselves, which means half of the data lies before the median, half of it lies after the median. That also means, though, that between any 2 points on a plot, like between the min and quartile 1, that's a quarter of the points. And it's the same amount of data points as between quartile 1 and the median, which has the same amount of data points as the median and the third quartile hold. And the quartile 3 and the max also hold the same number of data points. So that's something really, really good to keep in mind. Okay, the other thing to keep in mind here is that skew will affect the actual raw value of differences for interquartile range, right? So what does that mean? Well, what I'm saying here is, if you have a left skewed distribution, right? We're going to see that the values on the left, if you were to run a calculation between the minimum and the median, or even between the minimum and the first quartile, which would probably be somewhere around here, that value, like quartile 1 minus minimum, is going to be a lot bigger than like the median minus quartile 3 here. Not in terms of the number of data points, right? Per what we said above, but in terms of the raw value. Like if you took the quartile 3 value and you subtracted the median from it. It's good to know that like a left skew will favor the different size of like the median and the minimum, right? If you do median minus minimum on the left side of the skew, if it's a left skew, you're going to get a bigger number than if you did like the maximum and the median on that same skew, right? Because the maximum value and the difference between it and the median are going to be slightly different or slightly off. Same thing with quartile 3. Okay, so these are good things to keep in mind. And then the opposite would be true when you have sort of a right-skewed graph. Okay, the last thing I want to talk about regarding box plots is that when you have a box plot and another box plot, okay, let's say I'm putting them on a graph. Oh, we disappeared. Let's say I'm putting them on a graph here. Okay. And let's say I've been a fool, right? So I've gone ahead and I've put my x-axis in the y-axis area, right, for frequencies. And we're going, and we're going. Now, I may give you questions where I ask you, hey, where do values lie? You know, where does let's say this is dog's speed and this is cat's speed, right? We call that speed on the side that we're calculating. Okay. Now, I may ask you a question where I'm like, which of the following is true? And I would say something like, 50% of dogs are slower than the top 50% of cats, right? The bottom 50% of dogs are slower than the top 50% of cats. And in this case, that would quite obviously be the case, right? You can see where the cats sit, their top 50%, versus where the dogs sit in their bottom 50%, right? Alternately, we do lots of comparisons where we'll look at like, oh, where did the top 2/3 of dogs lie versus the top 1/3 of cats. So this is just an example of, through comparison in a multiple choice problem, how you will have to understand how the percentage of data points where they lie, how that relates between two box plots. Okay, so remembering that we know how to compare amounts of data points and understanding that in context is going to be super, super, super important. Okay, another thing to keep in mind, stem plots. We haven't looked at a lot of stem plots in a minute, but something that you should be aware of is that there's something called a back-to-back stem plot. You've probably seen these before. Ooh, back-to-back stem plot. And what that would look like is like 1, 2, 3, 4, 5. And then you would have two sets of data, right? So if I were doing, again, dogs and cats, you would have data, I don't know if this is number of years that they lived to, you could have data points like this. Right? And then we would do the same thing with the cats over here, right? It'd be 1, and actually let's just give them vaguely similar values here. Okay. So when we look at these, remember that left is low. That is super important to remember actually on all quantitative graphs, but the further left you go on a skew, or you go when you're looking at the curve, that's the low end, right? So like this one here is the left side because it's the lower number, so 10 and 10. So on this dog one here, it looks like we've got a unimodal left skew because again, the lower numbers will be the left side, and that's where the tail is sitting. The cats, on the other hand, are maybe bimodal here. But that's important to notice that, right, with the cats, it's almost like the reverse of the way the dogs are sitting on this stem plot. So just remember to revert your look one way and then look at the other. And don't be afraid when you see a back-to-back stem plot. It's some basic stuff. Okay, so far we've just gone over medians, we've gotten comfortable with them, we've gotten comfortable with the way we compare them across box plots comfortably, and then we've looked at back-to-back stem plots. So nothing too crazy, right? For means and calculators, okay? This is super important, super, super important. You can tell I'm trying to fix my mean here. Okay, means and calculators. What's the situation? Well, I'm gonna give you extra data. Extra data is coming your way, that's a problem. That's a promise, I should say. So what I want you to be sure of in your mind and mind of hearts is that you are absolutely certain that you are not plugging in 0 and 1 when you're using a data point, right? Remember, when you're using a data point, you want whatever mean I give you and whatever standard deviation I give you, right? But for a z-score, make sure you are plugging in 0 for the mean and 1 for the standard deviation. That is super, super, super important, right? Don't plug in the mean and the standard deviation I give you in a problem if you're calculating a z-score. And do remember, if you're trying to find a z-score, to use the equation z equals x minus the mean divided by the standard deviation. Okay, these again, just some tips and tricks to keep in mind. Don't mix up your calculations and don't mix up the ways that you'll roll about these things. Okay, next thing, remember the empirical rule. Do not forget the empirical rule. Remember the vague distribution of percentages from the empirical rule, where we have the mean down the center, and within one standard deviation, we have 34% of data on either side. Remember to put that in and understand that, and remember it can be very useful to you in various problems, right? Remember that again, within 2 standard deviations, which is where we're at now, -2 and 2, and 1 and -1, just to make sure we're clear on all that. There will be, again, 13.5% coming around here, and the same on the other side, 13.5%. You can hear my little dude hanging with us. And then again, about 2.35% coming out this way, 2.35%. Wonderful. And that last little nib at the end is about 0.15%. Now, this is a hideous drawing, but of course you can refer to the empirical rule drawing from our slides, or you can look it up. It's all over the internet. That is the empirical rule. Know it, live it, feel comfortable with it. Ooh, that rhymed. I like that. I'm going to keep that as a phrase. Okay, we've had a lot of questions where we talk about transformations, right? So make sure you are comfortable with transformations and transforming data. that's where we change the mean and the standard deviation in various ways. But just be aware, you're probably going to run into a question where I say something to the effect of, there is a random variable x, right? And that random variable x has a mean of like 10, for example, and a standard deviation of 3. I'm just making up numbers. Excuse me. And then the question will say, imagine a variable y, where y is equal to some transition or some alteration to x. So in this case, we'll say 4 plus 3x, right? And then I'll say, what is y's mean, and what is y's standard deviation equal to? And you're going to have to remember that the mean is impacted by both the addition and the multiplication here, right? So we'll multiply first. We'll do the mean times 3 is 30 plus 4 is 34, right? And that's our new mean. And then you'll have to remember that on the other hand, our standard deviation is only impacted by the multiplying. So 3 times 3 here is 9. And that would be our new situation, right? So again, we took our mean. We recognize that to get from x to y, we multiply the mean by 3, giving us 30, and then we add 4 to it, giving us 34. On the other hand, our standard deviation is only impacted by the multiplication, so it's 3 times 3, which is 9, and these would be our new values. Don't get mixed up, and don't forget how those transformations work. Okay, we've already rolled through so much material, guys. These are just my tips and tricks. You'll know, of course, to go through all the old material and remember it. Okay, what is the mean? The mean, of course, is the average. The median is not the average. We went through that. What is the standard deviation, though? Well, I'm going to give you a verbal explanation of this that's really important. Remember we talked about in class the fact that the standard deviation is how far you have to go from the mean. To get a certain percent of values in terms of like the actual number of values, right? And that's where we set these standard deviations to be known as, right? Now I'm going to give you a really boring AP version because it could be useful, wink, wink, hint, hint, when taking my multiple choice assessment, right? Remember that the standard deviation is how far you have to go from the average to get a certain amount of results. And therefore, another way to say it is, the standard deviation is approximately the mean distance. Actually, I will write this out for you. How about that? It is approximately, and this will make sense, but it's good to see it in this hideous writing, approximately the mean distance between each individual data point and the mean of the data points overall. Now, I'm so sorry for the way that is phrased. Obviously, this phrasing up here makes a lot more intuitive sense, but let's break down what this means. Approximately the mean distance, so approximately the average distance between each data point, so the average distance between any data point on my curve and the mean of the data points. And that's it. That's all it is. It's the average of all of the distances of every data point from the mean, and that's it. It's literally that. It's a fundamental breakdown of what the average would be of all the data points from the mean, and thus we set our standard deviation accordingly. But understand this language and be able to recognize this kind of wording, because wink, wink, hint, hint, you will run into these kinds of verbalizations, and one's similar to this one, I should say, and you want to be absolutely ready to tackle them and go, oh, they're describing the mean here. That's what that is. Or in this case, they're describing the standard deviation using the mean. Okay, so I'll do the little sad blueberry beneath it. All right, remember, of course, the 68, 95, 99, 7 rule. Oh, I should have done lines between each of them, right? 99, 7 rule. Which doesn't just mean where the data sits, right? That's the whole rule about 2 to 3 standard deviations from the mean. Oh no! From the mean. On either side. That's where your min and max should sit. So your max should sit between 2 standard deviations and 3 standard deviations from the mean, and your min should sit between -2 standard deviations and -3 standard deviations from the mean. And if either of those does not prove to be the case, for any reason, we are done calling this normal. We say not normal. Okay? Like a weird kid. Just kidding. I've got a weird kid strapped to my body right now. My sweet boy. Okay, we've got that, we've got this, we've got the other. I've already reminded you about remembering this equation, but I will say it again. Z equals x minus mean over standard deviation. If you find yourself in a precarious situation where you're like, what do I do with the calculator to get this value? Check this equation first and make sure this equation doesn't give you what you want, and show your work. For every problem. I know time is of the essence and it's rushed, and you will get through the exam. You will do a brilliant job on the exam, I have no doubt, but remember to show all of your work. For percentiles, this is something people slip up on every once in a while, so I will remind you of it. Remember with percentiles what it is you are looking for. What do I want? If a question says, find the value that only 3% of people do better than, or find the score that only 3% of students score higher than, I do not want the 3rd percentile. I want the 90, oh goodness, I almost wrote the 93. I want the 97th percentile. Okay, so check your percentiles, check them. Make sure you are looking for the correct thing when you are going through them. These are tiny slip-ups people often make. A side note, we went over this when we were talking in one of the homeworks, but remember that running times, and really it is, there are a couple other instances, but running times are the biggest one. Running times work in reverse. I'll say work oppositely. Right, so as values go down, they're harder. And as they go up, right, they're easier. Which is to say, as the values go down, you are faster. Right? As they go up, they are slower. Oh goodness. Got a bit of a freeze here. There we go. Okay, so as they go down, they go faster, and as the times go up, they go slower. And this is all to say, don't let that mix you up. If I give you a question where I'm seeing who's the better athlete or how the runner is doing, remember that the running times as they go lower, that means you've done a better job. And as they go higher, you've done a more average job, or you've done a poorer job, if you will. And the last thing I want you to remember is the way that means behave when you have a skew. So we talked earlier about medians and skew, right? But remember that when we have, I am so bad at drawing skews. I'm learning this about myself as a statistics aficionado. This is my greatest struggle. So there we go. So this left skewed graph here. Remember that the mean follows the tail of the skew. The mean follows the tail of the skew, which means the majority of values sit on the other side of the mean. Okay, so in a left skewed distribution, mean is lower and values greater than the mean. There are more of them, I should say. Because remember, the median's in the middle, which means if the median's in the middle and the mean is skewing itself toward the left, then there are actually more data points above the mean than below the mean. And remember also then that the opposite must be the case. And this is super important. There will definitely be a question where you are asked to interpret something like this. The median would be here, the mean would be here, getting pulled to the right in this right skew graph. And as that is the case, the mean is higher. And on the other end, right, the majority of values are before the mean. Now that's something you could interpret, right, from the fact that the median is here, and if the median is the exact middle value, well, then the mean must be getting more values on the left of it if the mean moves over. But something good to keep in mind. Okay, we talked about the impact that skew has on mean and median and on number of data points. We talked about running times and how they're a bit finicky, so don't get messed up with them. The same thing with percentiles. We remembered to look at the way things are phrased to figure out what percent people actually want. What percentile am I solving for? We went over the equation z equals x minus, or data point minus mean divided by standard deviation, to know it, to live by it, and to try it if you ever feel stuck on a problem, right? We also remembered to use the 2 to 3 standard deviations rule when it comes to determining if a curve is approximately normal. It's also known as the 68, 95, 99, 7 rule, and that is important to note. And we can use that to figure out if things are or are not normal. We talked about this really fancy, annoying definition of what a standard deviation is, because it may be useful for a question and even on the AP test. We noticed the standard deviation is not just phrased in the wonderful way I like to phrase it, which is just how far you have to go from the mean to get a certain percent of the values. It's also approximately the mean distance between each individual data point, so each one, and the mean of all the data points. And you find that sort of approximation, and that helps you figure out how far you have to go to get various data points. So good to keep that in mind. We went over the fact that the mean is the average, whereas the median is always the middle number. It is never the average of anything. We also reminded ourselves when transforming data to double check that there will be some kind of question with x and y as these two different distributions, and to remember that center is impacted by plus, minus, and by multiply, divide, versus our friend standard deviation is only impacted by multiply, divide. We then looked at the empirical rule, which we agreed we must know and feel comfortable with. We also went over how to look at extra data and determine what it is we truly need. To remember that when we're working with a z-score, the situation is simple. The mean is 0. The standard deviation is 1, even if I give you another mean and a standard deviation. On the other hand, if you want to find the data point or work with the data point, we are dealing with a mean that I have provided for you and a standard deviation that I have provided for you. Exclamation point in this case means I have provided it to you. And we will find this value actually, so I won't give you that one. Good, keep that in mind. We've looked at back-to-back stem plots, which are just the same as regular stem plots, but they look a little uglier. Remember that the lower numbers are the left side of the distribution if you're looking at skew. So this dog situation would be left skewed. And if the cat situation looked like the dog one, it would also be left skewed, but it doesn't. It's closer to bimodal here. We also looked at this weird example with the two box plots where we were comparing where the 50% of results lay or 3/4 of results lay. And actually really quickly, because I'm realizing this one's a little bit too vague, let me be a little clearer with this one. What if I did this? What if I said for dogs and cats, I'm gonna change to green for this. What if the distribution looked a little more like this? Okay, and then cats would be all the way down here. Okay. What I could say is 3/4, and this is where it gets fun, right? I could say 3/4 of dogs are faster than 3/4 of cats. And I know this to be the case because if I look at the dogs, 3/4 starts at our first quartile and goes up, right? That's 3/4 of the data. This is where we go back to the whole remembering the parts of a box plot. And then for the cats, 3/4 of data sits right here and down. And as you can see, that is lower than it is for the dogs. And so that comparison would be an accurate one. So that's one thing to keep in mind. That's how we do that kind of comparison. And you are likely to run into a comparison like that on the assessment. And then, of course, we went over the different components of understanding where data sits when we talk about median and quartiles. Remember, always, 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 this is a side note, but always calculate the IQR when looking for outliers, if that's available to you. And use that rule like it's a gospel for you, right? The 1.5 times IQR, and either adding that to quartile 3 or subtracting it from quartile 1, because when you do that, it is the most functional way to determine an outlier. And we remember that the median is the 50th percentile. Okay, that's been a little all over the place, but these are my last minute quick fix notes for you. This is a good way for you to go back through a lot of the material we talked about and start to flex your creative problem-solving muscles. I am so proud of you. Welcome to the brilliant journey of problem-solving through statistics. It's an honor to shepherd you through it. You're going to do brilliantly on this exam, and thank you for reading through these Unit 1 pro tips. This is Mr. Mays, signing out.